Hey, hello, this is Bob Jackson with Integrative Science, SC201. This is Chapter 3, the energy unit. Okay, energy is important, of course. Um, but when we get to talking about energy, we also get to talk about work and power and, um, and then a lot of things that we use energy for. Okay, energy is very important in the world by all means. In fact, modern society would not be at all the way it is if it wasn't for our energy resources, a very, very big factor in our national and world economies. Okay, so anyway, that's what this unit is on. We will do just a little bit of math. We're not going to do a bunch of math in this unit because this, as with the like when we were doing the Newton's laws of motion and so forth, we kind of reserve a lot of that math for the higher levels in science. Okay, so anyway, this unit's on energy mainly is the main thing, but like I say, you get into talking about work and power and the different types of energy. Okay, so let's go at it. Okay, first thing we talk about is work. Rather than not saying like we're going to work, but we're going to talk about work as it is defined in science in regards to use of energy and forces. Okay, so work is done on an object. We always talk work being done on something. You're not doing any work if you're not working with something, an object. Okay, and work is done to do something, and that is to move it in some kind of way. Okay, that move can be across from one point to another, or it can be like making the wheels turn on something. Okay, but in order for work to be done, something has to move. Okay, or work's not done. Like if I take and go over this wall, push on, sweat and everything else. But I've done no real work unless I move that wall. Okay, so now then, so work, technically you get into it, is a force applied relative to the distance it moves. Okay, so you apply a force and it's gonna move. Okay, if it moves, if it don't move and that's zero, then you've done zero work. So distance moves zero, you take force times zero, it's zero. Okay, so work is W, F is force, and D is distance. Okay, now force we typically measure in pounds. Okay, in English units, if we go metric, we talk newtons. So we give Shirazi some credit here. Okay, distance is measured in feet as far as English units, meters or centimeters when we're metric. Okay, so you could talk work units for when you actually solve a problem for work and the amount of work done. You would say the answer would be in foot pounds if it was talking about English units, but it'd be Newton meters if it was in metric. And then a Newton meter can also be called a joule, where you'll see a J. So if you see an answer of J for the work done on something, it is actually the same thing as a Newton meter. Okay, so that's work. Okay, we do work with simple machines. Okay, and there are 6 simple machines, and these are very much elementary level understanding. Okay, because they simply just recognize things that are types of simple machines. Your simple machines are levers, pulleys, wedges, inclined planes or a ramp, wheel and axle, and screws. Those are the simple machines that make up all the complex machines in this world. Okay, like a lever, it's like a pry bar, but a lever can also be a screwdriver. Okay, something you use to pry something. A lever is a breaker bar or a big long wrench to get a bolt undone. Okay, that's a lever. Okay, whereas pulley systems are stuff, pulley system, you're lifting stuff up or you're turning things like on your mower, on the mower deck, you have pulleys on there and a belt on them. That's making the blades turn. That's a pulley system. It is a simple machine. Okay, wedges, most common form you see is splitting wood. Okay, but it's a wedge-shaped, triangular-shaped piece of metal that you can split wood with. But you also use them in other applications as well. Whereas inclined planes are ramps, either ramps to load stuff or ramps for wheelchairs. Okay, for people with disabilities, which I had a disabled daughter, and we had her in a wheelchair, and we went everywhere with her. Okay, wheel and axles, that's like the wheels and axles on your vehicles, okay, or any carts. Okay, and then of course, I don't think screws take much to explain what they are. Okay, so now then, when you're working with simple machines, we use machines to make things easier for us. And we use them because they give us mechanical advantage, which we can just call MA. Okay, the MA can be mathematically determined two ways, either through a measure of distance or through the input force that we put into it. Okay, input and output. Okay, so MA is the distance, the effort distance or input distance divided by the resistance distance or output. A lot of times you'll call your book calls it DE. Input distance, output distance. Okay, so like a pry bar has an input distance, how long that pry bar is. Output distance is typically short, that is prying up on something. Okay, so you talk a distance, which is usually length of the tools to the what you call the fulcrum, the point that they pivot. Okay, and then you could also measure in regard to the force that you put in. Okay, so how hard you're working. You have resistance force, which is output force, which is typically the weight of the object. To your input force or effort force is how much force you're output in to lift whatever up. Okay, so that's how you determine mechanical advantage of something. But mechanical advantage is just how much easier it makes you. If you want to know what the mechanical advantage is of a device, is where you're determining how much easier it's going to make the job for you. Okay, so next page here. Okay, now in here, we're actually doing some math, which is easy math to work math. Okay, how much work is done by a hammer that exerts 950 newtons? Okay, which that hurts your finger when it hit it with 950 newtons of force. Okay, needless to say. On a nail, and the nail is driven into the wood 2 centimeters. So you always have a force and a distance, because work is equal to force times distance. Okay, so I got my force of 950 newtons, my distance of 2 centimeters, which would be 0.02 meters. You do want to put it in meters. If I convert 2 centimeters to meters, I'm dividing it by 100. So that'd be 0.02 meters. So then work will equal 950 newtons times the meters is 19 Newton meters, which we can also call joules. Okay. Here we got another problem. We say a force of 200 newtons is, I should say, needed to push a table across a room a distance of 2.5 meters. How much work is done on the table? So I'm taking the 200 newtons, and it's moved a distance of 2.5 meters. And I'm asked to calculate work. So work will equal 200 newtons times 2.5 meters. That gives you 500 newton meters, or you can say 500 joules. Okay, now those problems aren't bad. Okay, here's another work problem. Got this guy pulling on this, wanting to know what distance going to pull. So if you put 20 newton meters or 20 joules of work on an object with 500 newtons of force, how far will you move the object? Okay, 500 newtons of force. You did this work on it. How far did it move? Distance will be work divided by force. So I take 20 divided by 500. 20 is the work number, and 500 is the force in newtons. I get 0.04 meters. Okay, which isn't that far, but it did some work. It moved. Okay, simple machine math. These are the easiest ones of all, because you're taking a big number divided by a little number on each one of them every time. So it says calculate the mechanical advantage of a simple machine that has an input force of 15 newtons and an output force of 60 newtons. Okay, every time on on mechanical advantage problems or MA problems, you take the big number divided by the little number. It doesn't matter whether you're talking force or you're talking distances. Okay, so FR is the resistant force, okay, is 60. The input force is 15. So I take 60 divided by 15 and it gives me 4. All MA values are always going to be typically smaller numbers. Okay, and most of the time they're whole numbers. Okay, not decimal places on them at all. So now what that means is this machine makes this job 4 times easier. Okay, I use a fourth amount of energy to lift that thing up because of using the machine. Okay, so down here a lever, here's a pry bar. Okay, here I'm saying that giving you lengths of it, saying any given situation has an ever distance to the fulcrum where the work's being done is 24 centimeters. The output resistant distance is 8 centimeters. Okay, so like I said, you're always going to take the big number divided by the little number on these to get your answer, and the units are always canceling out, so you end up unitless. So you take 24 divided by 8, and it comes out 3. Okay, that's simple machine math. Pretty easy problems. Okay, here's a pulley. This is a simple machine. It says have a pulley. That's spelled wrong. Should be EY. Have a pulley system is used and 1,400 newtons of force are exerted by a person to lift 4,200 newtons. Okay, what is the mechanical advantage of the pulley system? Okay, you're going to take big number. You're going to take big number divided by little number to get your answer. Okay, resistance force, input force, big number divided by little number, there's your answer. Okay, that did come out in between. Most of the time they come out where they are a whole number, but they can come out decimal places. Okay. Now here's energy. We want to talk different types of energy, and that's about all the further we're going with energy, is different types of energy and forms of energy we use every day. Okay, so energy is simply the ability to do work, and it takes a lot of energy to do very much work. I mean, it just does. And energy is so important today. When work is done on an object, a change in energy occurs somehow, a conversion of energy. Not you don't lose energy, you never destroy it, but it's changed. Okay, some key things I want you to understand are some forms of energy without getting too wild with, because you can go into several different types of energy actually. The main 2 types are kinetic energy and potential energy, and I would very much like for you and get your students to understand those are the 2 main types of energy. Kinetic energy is energy of movement, energy of motion, action. Potential energy is stored energy or energy of position, you'll see it called, but I prefer to call it stored energy. These are each stored energy forms or potential energy forms. Chemical energy, like a battery. A battery is chemical energy where you have energy stored in that battery. That's why we use a battery to get electricity out of it. You have elastic energy, like winding up a rubber band or then wind up toys to make them go. That's elastic energy. Then you have nuclear and gravitational energy. Okay, these we deal with very little, in most part from day to day, nuclear, gravitational. Nuclear is like a nuclear power plant or a nuclear sub. Okay, and then you got kinetic energy, can be anything from heat energy to mechanical energy, like the runnings of a machine. Okay, electrical energy by far is our most common energy that we talk about every day, and that's what the rest of the this unit I want to have you know really anything about is electrical energy and how we use it. And then magnetic energy, and really putting the 2 together, electrical and magnetic energy, called electromagnetic energy, is really important. Okay, so now then we're going in this law of conservation of energy. Energy is never created nor destroyed, no matter what we do. Okay, and that is one of the most important things to ever understand about energy. Okay, now that's really the only definition, besides knowing a definition of energy, that I really push to the elementary kids know. Now, the big thing that we want to get into is really talk about energy use in the United States. And this is all predominantly electrical energy. You can also talk energy as far as cars and using gasoline and so forth, but that's probably gets a little overwhelming for students, but they can understand using stuff that are turning on and off at their houses using electricity. So energy use in the US is one of the more important things to get to understand and understand what items that use the most energy around us. And that's typically heating and cooling, okay, and even like water heaters. Those are the biggest consumers of electricity that we know, okay, in our households. And getting control of them can save us lots of money, okay, whereas these other items use, but not nearly as much. Okay, and that's where the kiddos see this, well, then I can just plan my computer 24 hours a day. Don't use that much electricity, but it does. Okay, lighting used to be one of the higher ones until LED lights come out. Okay, so I would push more for your kids to understand the things that use energy. Okay, and that costs us. Okay, major sources of energy. Okay, and this is where you can go to whatever degree of doing projects and stuff in class is you go from your fossil fuels to your renewable energies that are not totally away from fossil fuels. Okay, and we're seeing big changes in this today, just like in Indiana, we're seeing a whole lot more wind turbines up north and even a whole lot more solar fields coming about. And this is a breakdown from 2009 to 2019. It's the latest real good data I could find and showing the breakdown of this. If you look, we use natural gas, and these are all to produce electricity. Okay, natural gas was at this level in 2009, but if you look now, we're using a lot more natural gas to make electricity. Okay, and that's where we have a lot of natural gas plants popping up around and less coal-fired plants. Okay, that's where you see here 21% of electricity being produced by coal burning. Here you went down to 18, and then the coal is only 11% here. 2019, it's going down quickly. Coal-fired power plants is what Indiana was famous for, and you're seeing there's less of them as they go. Kind of neat when they blow up some of these plants and take down the stacks. But I've been in several of the power plants, the coal-fired power plants, but there's getting less and less of them. And that's one of the things we want to talk about, energy. We get our energy from our power plants. The electricity comes to our houses across the power grid. And it wouldn't be bad to talk the power grid to them, how the electricity gets from a power plant to you. Okay, and then you're paying a bill for that, of course. Okay, and then this is the last of it is I'd like for you to be able to differentiate to your students in regards to energy, what are renewable energies and what are non-renewable. Your fossil fuels are all non-renewable. We're using them up faster than what they can be naturally made. Whereas renewable energies are truly renewable. I mean, we aren't using them up, and that's wind and hydropower, solar, geothermal, and biomass. Biomass, we're taking natural gas off of landfills and burning it to make electricity, or even just burning it to create heat to use in like brick plants. Okay, so, and that's it. That wraps up chapter 3, and have a good day. Look forward to seeing you in class.